Welcome to our ME Lab refrigeration presentation. We are Group 1. The team members are Aiden Brook, Coben Miles, Yang Nguyen, and Michaela Sinclair. Machine Chiller has hired Burdell Incorporated to provide an independent review of the newly developed cooling system based on compressed air flow through a vortex tube. The goal of the experiment is to characterize the system and determine its cooling capabilities. The physical setup of the experiment is depicted here. Compressed air either from building supply or a compressor is regulated and fed to the heat exchanger at Station 1 and into the accumulator tank at Station 2. The compressed air flows to the vortex tube at Station 3 where it splits into hot and cold stream at Station 4. The cold stream flows through and cool the load before dissipating into the environment at Station 5. Station 1, 3, 4, and 5 have independent measurement devices such as temperature, pressure, and flow rate sensor. The working details of each station are depicted in the next slides. A DC motor turns a piston cylinder compressor, which sucks in low temperature and low pressure air and discharges high pressure and high temperature compressed air through a reed valve. Compressed air from the compressor is fed into the heat exchanger, where the temperature is brought down to near ambient, while maintaining the pressure. The air is stored in the accumulator tank, which helps maintain a steady pressure. Air from the accumulator flows into the vortex tube, where it separates compressed air into hot and cold uncompressed air. The cold air flows through and cools the styrofoam insulated aluminum load, and the heated air is discharged to the environment. Testing and analysis are distributed over 2 weeks. First week focus on characterizing vortex tube relationships, load steady-state heat transfer, motor speed versus pressure relationship, and heat exchanger accumulator effectiveness. Second week focus on characterizing load to transient heat transfer and uncertainty analysis. Week 1 procedure. To characterize vortex tube relationships and low steady-state heat transfer, building compressed air at 0, 20, 40, 60, and 80 psi is sent to the accumulator without a heat exchanger, to the vortex tube, and to the load. The temperature of ambient air, station 3, 4, 5, and the load are measured. The pressure at station 3 and the flow rate of hot and cold air at station 5 are also collected. Next, to characterize motor compressor and heat exchanger accumulator, a potentiometer is used to vary the motor speed and the accumulator pressure are observed. Air passed through the heat exchanger in this experiment. The data are collected similar to the previous part. Week 2 procedure. To characterize low transient heat transfer, building air at 80 psi and compressor air at 40 psi is sent to the heat exchanger, to the accumulator, to the vortex tube, and to the load. The data are collected similar to the previous part.
And that wraps it up for the materials and methods section. Next up is the results from week 1 of this lab. We have recorded and analyzed data for different pressures that are inputted into the vortex tube, which include 20, 40, 60, and 80 psi. Here are the results for the 20 psi case. On the top row, you can see the verification that T3 is roughly the same as T ambient, within a few kelvins, along with the load energy balance showing the hot and cold temperatures for T4, the load temperature, and T5. On the bottom row, you can see the pressure at 3 plotted against the same temperatures as the load energy balance, and next to that, you can see the mass flow rate of the hot and cold exits of the vortex tube. These next graphs are for the 40 psi case. You can see on the bottom row that M cold sits around 3.2 times 10 to the negative 4 kilograms per second, and hot at 2.875 times 10 to the negative 4 kilograms per second. The temperatures for T4 cold, hot, T5, and T load are 277 Kelvin, 314 Kelvin, 286 Kelvin, and 290 Kelvin respectively. Shown here are the graphs for the 60 psi case. On the bottom, you can see that mass flow for cold and hot sit around 4.5 times 10 to the negative 4 kilograms per second and 3.6 times 10 to the negative 4 kilograms per second. The temperatures for T4 cold and hot, T5, and T load are 269 Kelvin, 324 Kelvin, 287 Kelvin, and 279 Kelvin respectively. Finally, here are the graphs for the 80 psi case. You can see the mass flow rate for the cold and hot exits of the vortex tube are 6.4 times 10 to the negative 4 kilograms per second and 4.26 times 10 to the negative 4 kilograms per second. The temperatures for T4 cold and hot, T5, and T load are about 266 Kelvin, 332 Kelvin, 288 Kelvin, and 277 Kelvin respectively. Here is a table containing the pressure at 3, P3, T4 for hot and cold, T5, T load, and the mass flow rates for each PSI case, along with their graphs for each hot and cold data values. You can see as pressure increases, mass flow rate for cold increases, but decreases for the hot case. You can also see as pressure increases that P3 and T4 hot both increase, while T4 cold, T load, and T5 all decrease.
The motor and compressor will first be characterized by verifying that they are indeed in the steady state region. Looking at the three graphs for the 0 psi, 20 psi, and 40 psi case, it can be seen that the graphs are at steady state due to the horizontal nature of the data. The motor and compressor was tested at nominal psi values of 0, 20, and 40. These were ran at motor speeds of 0, 1076, and 2140 RPMs respectively, and these produced P3 values shown in the table. These P3 and motor RPM values were graphed against each other, and a fairly linear fit can be seen in the graph. To characterize the heat exchanger as working well, the P3 values must be constant, and this is shown in the graph on the left. Also, the T3 values should equal the T ambient values. With a T ambient of 294.9 degrees Kelvin, looking at the graph, our T3 values go no higher than 300, which is within 5 degrees, and the T1 values after the first data point increase very quickly above the T3 values. The theoretical thermal resistance was calculated using the equation L divided by K times A. The values are listed below. This theoretical value was calculated to be 26.440. The Q ambient theoretical was calculated using the equation 1 over R times T ambient minus T load. The experimental thermal resistance and ambient energy, as well as the theoretical ambient energy values, are found in the table below. They were calculated for nominal PSIs of 20, 40, 60, and 80. Notably, both Q ambients increase as the nominal PSI increases, and the thermal resistance finds a peak at the 60 nominal PSI value of 1.8.
So in conclusion, the experimental Q ambient or Q error steady state is greater than Q ambient. Reasons for differences in these values could include Rn calculated with measured values with their respective uncertainties and M code calculated with V hot at their respective uncertainties for measured values. A higher thermal resistance is ideal for aluminum insulation. The experimental thermal resistance values shown on the previous slide are at standard value. For week 2, our focus is on the transient response of the system. We're hoping for decays to 0 to show stability and lower Q error rather than growth, which will show instability and a greater Q error. The goal is to come to a conclusion of validity of the system modeling to satisfy the client's desire for an independent review of their system.